In this video, we're going to look at range and trajectory, specifically a couple of specialized equations derived to figure out that the motion of a projectile follows a parabolic shape and get something we call the range equation. And I admit that this is an exciting and useful equation. And there are a lot of problems that can be solved more easily with it, but it's not a required thing. And it's certainly not something that will be on your AP equation sheet. So either you memorize it, learn how to use it, or you don't, and either way is fine. So the first kind of record we have of understanding, at least in Western thought, was of these parabolic trajectories was Galileo. The prior explanation was this impetus idea that things would sort of travel in a straight line and then it would run out of that whatever quantity it had and then fall straight down. And this is sort of a common mistake that we can do, a misconception when we're starting to think about this, thinking that a velocity vector also points in the direction it will always travel. But when there's acceleration, it goes in this sort of constant free fall state. More about that when we get to orbital motion too, because it's essentially free fall around a planet. The equation for a parabola follows this form: y equals ax plus bx squared, where a and b are constants. And if you look at this, you'll probably realize that if you replace that y with a position variable and the x's with time, you sort of get something that reminds us of our kinematics relationships with constant acceleration. Specifically, if we plug in these relationships, we get x equals vxt and y equals v naught yt plus 1/2 gt squared. And the parabola equation doesn't really have anything with time, right? And so what we're going to do is we're going to combine these together because this is a physical space sort of relationship we're trying to figure out. And so if we combine them together, we get rid of time, we can solve. And this is kind of clicking around, plugging in for time there. We get this ratio of v naught y over vx and g over 2vx, and we can recombine these into these constants. And so we get the basic idea that projectile motion is parabolic. And we can, instead of talk about x and y components, we can talk about the initial velocity, which is at some angle, and the angle itself. Of course, these ratios here are going to relate to those quantities anyway, right? The y component over the x component is the tangent of theta, and the x component is v cosine theta. G is a constant here, and so if we put all of this stuff together, we get an equation that is not an AP equation. You don't really need to know it, but it is a useful relationship. Specifically, what we can do is get a range equation. This is a very special case, and the special case is that we have a distance in the x direction we call capital R the range. Downrange is the phrasing that relates to. And it only really works when we're talking about the delta x, the displacement in the x direction, when the y values, initial and final y position, are the same height. There's another more complicated equation that can deal with different heights, but we're not going to worry about that one. So what does this depend on? Well, it really only depends on the initial velocity and the angle. And so if we put this together, an equation for r in terms of v naught and theta, move myself out of the way, we get r is vx times t, and vx is v naught cosine theta times time. And again, with time, we can rearrange one of our kinematics equations to solve for time with that special case. If we plug that in, we end up with what we call the range equation, which is the initial velocity cosine theta times all this other stuff. We can simplify that a little bit, right? 2 sine theta cosine theta is a trig identity, which is sine of 2 theta. And we end up, if we let g just be the absolute value of g, right, which is the magnitude of the acceleration, we get range is v naught squared over g times a sine of 2 theta, which is a relatively simple equation. And this is what we call the range equation. So if you know the initial velocity, you know you're on a planet with a constant acceleration due to gravity, in this case, little g for Earth, and you know the angle that you launch at, you can make some predictions. There's some really interesting results of this, though, and that is that this only works if we're going from the same height to the same height, and it provides us some insight, specifically that if you double the speed, it goes 4 times as far, right? Double V naught squared gives us the range. If you change the G by some factor, that changes R by the reciprocal of that factor, right? And when is R maximum and minimum? Well, for a given V naught and G, when is sine of 2 theta maximum and minimum? Well, here's an example to help us think about this. If you launch a projectile at 40 meters per second over level ground and it lands 100 meters away, what is the launch angle that is needed to make this happen? And so if you think of this as sort of a targeting problem, I want to hit a target with a projectile. I know my projectile launcher launches at 40 meters per second, and the distance away I need to hit is 100 meters. So we're solving for what angle to fire at. We can solve this for the angle, and we find that the sine of 2 theta is 0.612. We can use an inverse sine, and we find that we need an angle of 37.8 degrees, which is about of 2 theta of that, when theta is then 19 degrees. So a launch angle of 90 degrees. But the question is there another correct answer? Because we know trig functions are periodic, that you get the same value out of them with different inputs. And so where else is sine of 2 theta equal to that? Sine of 2 theta and sine of 2 theta equals 180 minus that 38 would be at 142 degrees, right? So theta is 71 degrees. So in other words, there's 2 different angles you can fire at, a low angle and a high angle, that will get you to the same place, which is interesting. Now, of course, as we talked about previously, the higher you fire it, or the more the y component is, the longer it will be in the air. And if you want to hit the target faster, you should go with the shallow angle, right? So basically 45, which would be halfway between 0 and 90 degrees, plus or minus that 26 degrees will get us our value. And so this is what's called the sprinkler effect. If you take a bunch of different angles, fire your projectile at all these different angles, you find that there are multiple places, right? 45 degrees gets you your maximum distance, but for every angle between 0 and 90 degrees other than 45, there are 2 angles that will get you to the same place. One will do it quickly with a shallow trajectory. One will go up in the air for a long time, but eventually hit that as well. So that's kind of the range equation. The equation itself is pretty simple. You can try to apply it to some of the problems we practice solving. If you want to read more about this and other stuff with range and trajectory, Chapter 4, Sections 1 through 6.